Another problem we examined is the sensitivity to beta-lactamases. And here it's quite simple how to solve it. And so simply we can insert bulky groups on our R moiety, and that will prevent the penicillin analog from binding to beta-lactamases. An example of that is the methicillin here, which basically is a derivative of penicillin G, in which we have two ortho groups here that block the access to beta-lactamases. And the trick is to make sure that the substituents block access to beta-lactamases, but not to the transpeptidases. Another good example is oxacillin. We already talked about that, which is basically has a group that covers more than one function. It's bulky and it's also electron withdrawing, and so yields at the same time oral activity and also resistance to beta-lactamase. And we also can further decorate and functionalize the aromatic ring with a bunch of substituents, making it even more active. Broad spectrum penicillins, which are more potent against gram negatives, tend to have a amine here, the alpha position, and so ampicillin and amoxicillin are some of them. We can use them as a prodrugs, and so in doing so, what we do is functionalize another moiety here, the carboxy group on the ring, here's the beta-lactam ring, and these prodrugs are hydrolyzed by esterases in vivo. So the way it works, you will notice, is that they have actually two ester group functionality, one attached to the group and the other one further downstream, and that in turn makes it easier for esterases to function and to cleave off this drug. So let's look at it in more detail. If we made the ester directly attached to the penicillin, then that will be difficult to cleave, but by moving it out a little bit, we make the enzyme more, facilitate the role of the enzyme, and so, facilitate attack on this carbonyl. In turn, then we get this moiety, which basically is very susceptible to rearrangement to give formaldehyde, which remember looks like this, and the free carbonyl group. And so that happens in the body, and basically these prodrugs are used to facilitate the absorption of penicillins through to the gut. So other examples of broad spectrum penicillins contain an extra carboxyl group here. So a carboxylic acid typically, and so these are called the carboxypenicillins. They're active with, again, gram negatives, and they tend to be resistant to beta-lactamases because, again, that group affords enough bulk to prevent binding. So with that, we kind of finish off talking about penicillins, and then now I want to discuss cephalosporins, which derive from the same biosynthetic pathways we discussed in the synthesis of penicillin, but now the nucleus is a little different, and mainly we have this penta atom ring now becomes an hexa atom ring, and so expansion of that ring changes the properties slightly and makes them more resistant to beta-lactamases. One should note, though, that the activity of cephalosporins is generally lower than that of penicillins. However, the increased resistance to beta-lactamases makes it worthwhile. We have the same beta-lactam ring. We call it now 7-amino adipic side chain here. And we have this dihydrothiazine ring, which contains a double bond. The position of the double bond, as we will see, turns out to be very important. We can use this 7-amino cephalosporonic acid as a precursor in the biosynthesis of different cephalosporins, so just like we did before. The structural activity relationship is very similar to that of penicillin. We still have the presence of beta-lactam. We also have that the position, the carboxylic acid in this position is important. The bicyclic system is important once again because we are increasing ring strain on the beta-lactam, and that's where also the double bond is important. So we have different classes, which we call them generations, first, second, and third and fourth generations. And we now have a little bit more variability because we can functionalize both this group here and this group. The mechanism of action is identical to penicillins, really, so the only variation is that there is a rearrangement of the covalent adduct to release acetic acid. So cephalosporins are important because they can inhibit beta-lactamases, and so we can have this inhibition that is either transient or permanent. And the reason for it is that the hydrolysis of this intermediate compound, which has rearranged, is very slow. So starting from a 7-ACA, we can use the same chemistry we've seen before to functionalize the cephalosporins. Now the only difference is that 7-ACA needs to be made chemically with the same procedure we saw before, using phosphorus pentachloride and then generating the amino ether that then gets hydrolyzed to 7-ACA and then functionalized to give penicillins. So once again we have first generations, as you say, so cephalosporins are also natural products. The specificity is a little different, and in particular, first generation, one of these cephalothin is more active against some gram negatives. In general, they get metabolized with the same overall chemistry, and the first thing that happens is that we basically hydrolyze the acetyl group here on the side chain in position 3, and then we have compounds that are less active. So several derivatives are known, and the important thing is, again, in the rearrangement, that we have a decent leaving group that allows for the formation of the covalent intermediate, both with beta-lactamases and with transpeptidases. So I'm not going to expect you to remember all these derivatives. The main points that we are making here is, again, how they can be synthesized. For example, they can be synthesized from penicillins by ring expansion, and I don't expect you to remember the chemistry, just to know that it's doable. And again, we have several generations of cephalosporins. They change by their overall properties. In general, again, resistance to beta-lactamases and resistance to esterases in this case, because we now have an urethane group, and the spectrum of activity also is important. So yeah, we have this third generation, then basically puts together several of the changes we already seen, and also explores the chemistry obtained by substituting in these side chains. And then finally the fourth generation. As you have noticed, basically the position of the double bond is very important here. The fourth generation has a way more complex substituents here on position R. So overall, they all look the same way. So penicillin and cephalosporins have the same beta-lactam activity. functional group, and then the structure and space can look a little bit different. All of them mimic diala-diala conformation. And in fact, in cephalosporins, we have the loss of activity if we change the position of the double bond, again indicating that the three-dimensional structure of these antibiotics is indeed very, very important. So what we are doing by changing the position of the ring is changing their shape, and so making them inactive. So here we have the difference in activity that we have when we change the different conformation rather that we have between the cephalosporin with the position with the ring, the double bond in this position versus penicillin. And you can see that delta 3 cephalosporin, which is active, has not basically not a different stereochemistry, but rather what it has a different three-dimensional conformation. The bioactive conformation is the one of the two basically almost isoenergetic conformations. We have two in which the carboxylic group is either pseudo-axial or pseudo-equatorial, and the activity is correlated with the pseudo-equatorial one. So penicillin actually contains an active conformer, which is different from what we've seen before, the inactive conformer, and that is very similar to what we have with the delta 3 conformation. So with that, we can extract a useful parameter also that helps us decide whether or not a penicillin analog or something that contains a beta-lactam ring will be active. And that's the distance between the carbonyl group of the beta-lactam and the carboxylic group here, the carboxylic acid derivative. When the distance is below 4 angstroms, then we have compounds that are active. This works in all beta-lactam derivatives. For example, this one called sulfazesin, which is contains only the beta-lactam ring, no fused ring. But again, we have the distance between the two groups that is below 4 angstroms. We do have some monocyclic beta-lactam derivatives, and those are tend to be resistant to beta-lactamases. They're all natural products, but they also can be produced by synthesis. Okay, so with that, we pretty much covered beta-lactam antibiotics, and in the next video, we'll cover antibiotics that also act on the cell wall by a different mechanism.